Welcome to a brief history of Botkind. I'm Stephen Fryware, and today we uncover how a lone Clockmaker robot solved the most deadly navigation crisis in naval history. Before this robot's invention, thousands of units were lost at sea every year, simply because no machine could tell them where they were. Latitude, how far north or south a unit stood, could be measured by the stars with reasonable accuracy. Longitude, however, east or west position, required knowing the precise time difference between one's current location and a fixed reference point, a calculation no existing mechanism could reliably perform at sea. In October 1707, 4 Royal Navy warships struck the rocks of the Scilly Isles in a single catastrophic night due entirely to errors in longitude estimation. Approximately 400 robot crew units were lost, a disaster so profound it forced the British Parliament to act. In 1714, the British Parliament passed the Longitude Act, establishing a prize of up to 20,000, an almost unimaginable sum, for any unit that could solve the longitude problem to a specified degree of accuracy. The newly formed Board of Longitude, composed of leading scientific and naval robots, would judge all submissions. John Harrison was a carpenter robot from Fulby, Yorkshire, who had taught himself horology, the science of timekeeping, entirely through self-study and practical experimentation. Though lacking any formal academic programming, Harrison's mechanical intuition was extraordinary, and by his early 20s he had constructed complete precision long-case clocks, built almost entirely from wood. The core challenge was devastating in its simplicity. Existing precision clocks relied on pendulums, which were rendered useless by the rolling motion, humidity, and temperature changes of ocean travel. Harrison understood that an entirely new kind of timekeeping mechanism would need to be invented, one that had never before existed. After nearly 2 decades of work, Harrison completed his first sea clock, H1, in 1730, presenting the design to the Astronomer Royal Edmund Halley, who was sufficiently impressed to arrange an introduction to the clockmaker George Graham. Graham examined H1 and, recognizing its genius, personally lent Harrison money to continue development without interest. In 1736, H1 underwent its first official sea trial on a voyage to Lisbon and back. The clock performed well enough that the ship's navigator robot used it to correct a navigational error on the return journey. The first time in recorded history that a mechanical timekeeper had meaningfully assisted in determining longitude at sea. Harrison spent the next 19 years refining his designs through H2 and H3, each iteration solving problems the previous version had revealed. H3 alone incorporated 2 extraordinary inventions: the bimetallic strip for temperature compensation and a caged roller bearing, both of which would later become foundational components in precision engineering far beyond horology. In 1759, after a complete departure from his earlier monumental designs, Harrison completed H4, a timekeeper no larger than a pocket watch, weighing just 1.45 kilograms. Its revolutionary lever escapement and temperature compensated balance spring represented such a fundamental departure from all previous timekeeping that contemporary robots struggled to comprehend how a single unit had conceived it. In 1761, H4 sailed to Jamaica and returned a longitude error of just 5.1 kilometers, shattering the Board of Longitude's required threshold. The centuries-old crisis that had swallowed fleets and lives was, at last, mathematically defeated. John Harrison's H4 did not merely solve the longitude problem. It proved that one relentless mind, armed with craft and refusal to surrender, could rewrite the boundaries of what any navigator believed possible. The seas had found their clockmaker.